Let's look at sound. First of all, sound is a longitudinal wave. This means that as the energy moves to the right, we will also see the crests of the waves also moving to the right. So in this case, the speed of our particle, the velocity of our particle, is parallel to motion of the wave. A longitudinal wave has wavelength and amplitude and frequency and speed. In this image, we can see the compression of the air molecules very close together at the crest, very close together again at the crest, very close together again at the crest, and then very far apart at the trough, and very far apart at the trough. So we see a wavelength from compression to compression, like from crest to crest, there is a wavelength. Now the relationship between wavelength, frequency, and speed, well, if speed is measured in meters per second, so it's measured in meters per second, and our wavelength, which we use the symbol lambda for, so this is a lambda, okay, that's what that symbol is, it's a Greek letter. It's wavelength, and length is measured in meters, and frequency, or F for frequency, is the number of waves or cycles per time, and so this would be 1 seconds for our unit. So if our speed is in meters per second, so speed is in meters per second, and I have meters and per second here, I can multiply my frequency and the wavelength to get the right unit. So let's check that. And the frequency would be 1 seconds, and the wavelength would be meters. And so that would give me meters per second. So the speed of a wave is equal to frequency times wavelength. And remember, the symbol for a wavelength is a lambda, Greek letter. The amplitude indicates the volume of the sound. Now, sound waves, just like any other waves, have a frequency, so that's how often, and they have a wavelength. That's the distance from one point on the wave to an identical point on the wave. So that would be the wavelength. Now, if two waves are approaching each other, those two waves will interfere with each other. So let's say that we have one wave, and it's very hard to draw longitudinal waves. So a lot of times, even if it's a sound wave, we'll draw it where it looks like a transverse wave, like this. So this will be our equilibrium or zero energy position there. And let's say another wave is coming at this one, and it looks like this. And we'll put the equilibrium position here. And so let's say that this green wave is moving to the right, indicated by that yellow arrow there, and this pink wave is moving to the left, indicated by that purple arrow there. So when these two waves interact with each other and approach each other, they will interfere with each other. And at this point, the two waves are on top of each other. And this constructive interference will give us a resulting wave that will be twice as tall and have an amplitude crest and a trough, that it's equal to the addition of those two waves. This is called constructive interference. The two waves have constructed a bigger wave. Let's look at our two waves again. This time the pink wave has a trough and then a crest. And if we look at each one of these as they move towards each other and they begin to overlap each other, we see in the end that we have a positive green wave and this negative pink wave, and when we add these two amplitudes together, we will get nothing. And so because the positive amplitude here and the negative amplitude here, when added together, so positive A minus A for amplitude is equal to 0. So we get a 0 amplitude for both of these two places in our wave. So when we have these two waves cancel each other out, they are being destructive, or we call this destructive interference. This destructive interference works for any waves: sound waves, electromagnetic waves, seismic waves, ocean waves. This is the principle that we use when we are going to create sound canceling headphones.